Okay, we are recording. We are continuing our discussion of section 12.3, double integrals over general regions. And in this third example from the textbook, we want to evaluate this double integral over a region D, where D is the region bounded by the line and the plane. By that line, y equals x minus 1, and and the parabola y squared equals 2x plus 6. Okay, so let me just comment on something here. So in this problem here, okay, this is the double integral, right? So we have several things that we need to do. First of all, we need to figure out, we're going to have to draw a picture, right, of our region D so that we can determine what the limits are, because ultimately, right, we want to have, hold on here, for this problem, in order to get the answer, we need to figure out what are our limits going to be. Well, actually, first we need to figure out, are we going to do dy dx, or are we going to do dx dy? Which order of integration makes sense? And then based on the order of integration, which is easier, then what are the limits? So this problem could, and then we have to do the integration. So this problem could, take, 10 minutes at least to do. It's a big problem, right? It's a problem that in order to do it, you really need to work through it carefully. So first thing we always need to do is draw the region. Now, if you go into, and let me just go back to the problem at hand. So we have the line y equals x minus 1 and the parabola y squared equals 2x plus 6. Okay, so let's use Desmos to help us graph that line and that parabola. Okay, Desmos is free, as you know. Let's use Desmos to help us. Now, actually, in the old days, we used to use the graphing calculator, right? And that's fine. You can still use your TI, if you have like TI graphing calculator, that's fine. But that parabola y squared equals 2x plus 6, you would have to write that as two functions, y equals plus the square root of 2x plus 6, and y equals negative square root of 2x plus 6. Okay, so in order to draw that sideways parabola. All right, so let me see here. I went to Desmos here, and here's what Desmos drew. And you see there, what's really cool is that y squared equals 2x plus 6, like using a graphing calculator, you'd have to type in y equals plus square root of 2x plus 6 and y equals negative square root of 2x plus 6 in order to get that blue sideways parabola drawn on your calculator. But Desmos, it's really nice. It just draws that. Okay, how many think that's pretty cool? How many kind of like Desmos for drawing functions? How many maybe use Desmos in calculus 2 to draw functions? Okay, Simon has. Okay. Mary has. I hear you, Mary. Yep. And Norina. Yeah. And so the region D is that region that is between, it's above, well, It's bounded by the line and that parabola. So what do you think is going to be very important to find between the line and the parabola? What do you think we're going to need to find in order to help us do the problem? What we drew the graphs. Okay, we know what the region D looks like, but what also would be important to find between these two functions, you think? What do you think would be important to find? Good, Logan. Well, not the, that's right, Logan, the intersection points. Remember, IB, we are finding actually volumes in section 12.3, but the region D here, we have to find the intersection points. And what's nice about Desmos is if you click on where the point is, whoops, hold on now, what's that? I don't know what that is. If you click on that point, see that? And click on the other intersection point, how about that, huh? See there? Those are your intersection points. Pretty cool, right? So what you'd have to do, the intersection points are 5, 4, -1, -2. If you were to find those intersection points by hand, what you would have to do is this, so y equals x minus 1, and y squared equals, I don't know why it does this. Come on now, come on, don't do that to me. Don't do that to me. Let me move that back here. Okay, y squared equals 2x plus 6. So, you have equation 1 and equation 2. So you can take y equals x minus 1 and substitute it in for x here on the second equation. And so if you did that, you would have, y squared. No, I'm sorry. I said that wrong. I went too fast. Y equals x minus 1 gets substituted here for that y, right? For that y in the second equation. So what you're going to have then, is you're going to have x minus 1 squared equals 2x plus 6. So that means x minus 1 times x minus 1 equals 2x plus 6. So x squared minus 2x plus 1 equals 2x plus 6. So then x squared plus 4x minus 5 equals 0. So hold on here, the 2x and the 6, I just brought them over to the left side. Actually, I have an error here. It should be y squared minus 4x minus 5. So you've done this kind of thing before, back probably in high school, finding intersection points. Okay, so now we have, hold on. Keep screwing this up. Hold on. Let me go out and back in. Hold on. Okay. So now we have x squared. Nobody's touching anything, right? All right. So x squared minus 4x minus 5 equals 0. How are we going to solve for x? Should we use quadratic formula on that? Or can it be factored maybe? Well, it can be factored. What are the factors? That's right, Yeva. X minus, I don't know, it keeps I don't know, it keeps changing. I don't know, are you seeing this? It keeps changing the size on me. Is it doing it on your view or is it just mine? I mean, hold on here. Come on. Let's go. All right. Okay, so X minus, right. So we have X minus 5 and X plus 1. That's right. So X equals 5 or X equals negative 1. Well, if X equals 5, if we take X equals 5 and then we substitute it in equation 1 for X equals 5 here, Y would equal 5 minus 1, which equals 4. So that means one of the coordinates is 5, 4, one of the intersection points. And we established that in Desmos. And if X equals negative 1, then Y equals, hold on. Yeah, Y equals negative 1 minus 1. And so there Y equals negative 2. So negative 1, negative 2 is the other intersection point. So these here, these are your points of intersection. So you can certainly always get your points of intersection this way, but you're welcome to use Desmos also to get the points of intersection. That's fine. That's perfectly fine. Let me just see here. Okay, okay. So now let's go back to the problem. Let's go back to the problem. I keep hitting the wrong button, but we'll get there. Don't worry. Let's go back to the problem. So now here in figure 12 is, for this problem, example 3 from section 12.3, here is the region, and they're showing you two pictures. The picture on the left, they're treating the region as a type 1 region. That's where your limits are. You have you treat the region as between a function bounded above and function bounded below. But in this case, on the left figure in figure 12, the function that bounds the region below changes after you pass, like from x equals negative 3 to negative 1, that the function below that bounds the region changes from the bottom part of the parabola, y equals negative square root of 2x plus 6, to the line y equals x minus 1. Okay, so the right now I want to just say this right. The top function is always y equals square root of 2x plus 6 throughout the entire region. That's if you treat region D as a type 1 region. If you treat region D as a type 2 region, as they do on the left, well, you have a function on the left and a function on the right. So, okay, they get x equals y squared over 2 minus 3 on the left and x equals y plus 1 on the right. Now, how are they getting that? Well, let's go back to the whiteboard. Okay, let's go back to the whiteboard. So, when y equals x minus 1, this implies that x equals y plus 1. So yeah, that makes sense. for the line being written that way when we treat the region D as a type 2 region. The parabola is given by, so that's, one part. The parabola is y squared equals 2x plus 6. But we can write that as y squared minus 6 equals 2x. And so y squared minus 6 over 2 equals x. So this is how they get those two left and right, the left and right functions in figure 12b. Now I'll mention here, if x equals y squared minus 6 over 2, x would equal y squared over 2 minus 6 over 2. And I have an error here. So x will equal y squared over 2 minus 3. Okay, and that is what they have there in the figure. So, right, so let me go back to the figure. Okay, now, is it easier to compute this double integral treating D as a type 1 region, as they show on the left of figure 12, or treating D as a type 2 region, as they show in the second picture in figure 12? Which is easier, type 1 or type 2 region for this double integral? So in the figure 12a, a type 1 region, we're integrating with respect to y first and then x. Jimmy, and IB, you're right. The type 2 region on the right there, we're integrating with respect to x first and then y. The problem is, I'll show you the problem. Let me just draw that figure 12a. I'll just draw a quick picture here. I'm not even going to label. I'm just going to draw just a picture of the region. Okay, so here's what the region looks like. Well, I actually have to put in a little more detail. I'm reconstructing figure 12A from example 3. Okay, x-axis, x-axis, y-axis. And you see, or say this the right way, so if we think of this point here, the function on top is always the same. But on the bottom, the function changes from the bottom part of the paraboloid to the line. And so if you hold on here, I've just got to find the right color. In order to do this integral, so what I'm saying is this: if you were to do this double integral where you're doing dy first and then dx, that's a type 1 integral. You would have to actually have a region d1, you'd have a double integral for that, and then you'd have another region d2. You'd have a double integral for that, because you'd have to have the sum of what happened there. Hold on. Did I lose my? Let me go out. Hold on. Did I lose every? Okay. All right. You'd have to have two double integrals to evaluate this, because the bottom function changes. It's this paraboloid, bottom part of it's this paraboloid on region D1, and then it switches over to the line. Are you seeing this? How you would need the sum of two double integrals? If you were to do a type 1 region, if you were to do that and compute this, this is what you'd have to compute. So the first double integral, the y limits go from the bottom part of the paraboloid to the top part of the paraboloid. The second double integral, the y limits go from the line, x minus 1, to the top part of the paraboloid. Now that is actually doable. I actually worked that out. And it does work, but it takes a lot of time. On the other hand, let me go back to that figure 12. If you were to treat region B as a type 2 region, then throughout the entire region, the left function is x equals y squared over 2 minus 3, and the right function is x equals y minus 1. Okay, there's no switching of functions. And so that would allow you then to compute that double integral this way. You only need to compute that particular double integral. You can get it done with one double integral. You see that? And the actual answer actually equals 36. So now we're going to look at some problems. We're going to look at some other problems, but I just wanted to point that one out to you. Sometimes it's easier to integrate with respect to one variable first than the other variable. Are there any questions on this example 3 from the book? Okay, I'm going to stop the recording and I'm going to do another example. Let me go ahead and stop the recording, but we're going to continue here to the next example. We'll do it in a new recording.